Welcome back to another lesson on trigonometry. In previous lessons we brought up the equilateral triangle and the square. Now we must talk about the pentagon. To begin, let's start at the center point and draw 5 triangles. Now notice there are 360 degrees in one complete revolution. And there's 1, 2, 3, 4, 5 different angles. So 360 degrees divided by 5 is equal to 72 degrees. Meaning each one of these angles is 72 degrees. There are 180 degrees in one triangle. So meaning each of these angles has to be 54 degrees. 54 plus 54 plus 72 adds up to 180 degrees. In fact, you can use the same reasoning and apply it to a polygon of any number of sides. Divide 360 by the number and then use the 180 degrees in a triangle to find these angles. Then simply by doubling it, so this 54 times 2 is 108 degrees. So that is how we obtain those. Now, watch as I construct another pentagon, this time upside down. I'm using this triangle template. It is an isosceles triangle, meaning this side and this side are equal to each other. This angle and this angle are equal to each other. This is a 36, 72, 72 isosceles triangle. So once I've traced out that length, I mark a point here. Then I match up this point and that point to draw that. Again, flip it over, match this point and that point. Okay, same thing. This point and that point. Okay. Notice, because this is a bit of a crude method, there's a little bit of an error, but it demonstrates the point. So, same pentagon, flipped upside down. Now, all right, what if I now trace out these triangles? I should have planned out a little better at the top, but that's okay. So, what did I say? This interior angle is 108 degrees, whereas this angle is 72 degrees, which makes sense because there's 180 degrees in a straight line. 72 plus 108 is 180. Now 72, 72, that means this angle here is 36 degrees. Very good. What if I were to cut the triangle along this line? Okay, so this is 108 degrees. These side lengths are the same because each side on the pentagon is the same length. Isosceles, same length, means these two are the same angle. They are 36 degrees. Okay, very good. Keep those numbers in mind, because next we're going to move on to similar triangles. Notice I have another template of my 108, 36, 36 isosceles triangle. So that matches up with this guy. Okay, what if I focus in on this. Now I'm going to scale it down a little bit. So see how I've taken this chunk out of our star and split it up into two similar triangles. Boom, boom. Now you can verify these are similar by rotating. Look, the angles match up. Good. Again, the angles match up. We have similar triangles. Now, if I define the side length of the pentagon to be 1, I can translate that over to my triangles here. If this side length is 1, that means this is 1, and this is 1. And this is also equal to 1. Now, I don't know what the length of this is just yet, but that's what we're going to find. My unknown quantity I'll call x, which means this length from here to here is also x. This is x, and this is x. We've established that these two triangles have the same angles. They are similar. So let's compare the long over the short. So the long side of this triangle is going to be x plus 1. The short side is going to be x. All right? And then that's equal to, well, the long side of this triangle is x. The short side is 1. Okay, we're comparing two ratios. The simplest way to do that is to cross multiply. So I'm getting x plus 1 is equal to x squared. By rewriting that, x squared minus x minus 1 is equal to 0. Now I have a second order polynomial. I can plug the coefficients into the quadratic formula to find x is equal to 1 plus or minus the square root of 5 divided by 2. If I punch this into a calculator, I'll find that approximately equal to 1.618 or negative 0.618. This positive value is important. When we're speaking about the side length of a triangle, we'll ignore the negative value. Negative length is not very sensical. This positive value, 1.618, we call that phi. The Greek character phi represents this special constant, sometimes called the golden ratio